This is Jack Jackson. In this video we're going to talk about this technique called logarithmic differentiation, and we're going to use that to give us a generalized power-exponential rule. Now before we go any further, I want to review just a little bit. We have the power rule and we have the exponential rule, and I want to compare and contrast those just a little bit. In the most basic form, a power function is a one-step function where you have a variable base and a constant power. An exponential function, the most basic form, is also just a base and an exponent, but this time it's the base is a constant and the exponent is the variable. So those functions behave very differently. Our base for exponential is always a positive number, and it turns out you've got basically two basic shapes. You've got increasing concave up when the base is bigger than 1, and you've got decreasing concave up when the base is between 0 and 1. And technically you could have it where the base is 1, but then that really wouldn't be an exponential function. That would be a constant function. We don't allow a negative base. Power rule, on the other hand, we can allow any real number for the power, but there are several different graph shapes, and we go over some of those in another video. So because these have different shapes of graphs, of course their derivatives are going to be very different, and the rule that you get for them turns out to be different as well. So as you will hopefully recall from earlier, the derivative of u to the n, where n is a constant, u is a variable, is n times u to the n minus 1, and then times the derivative of u. So here I've stated the power rule, but I put it in conjunction with the chain rule. We do the same thing for the exponential rule. It's the derivative with respect to x of b to the u, where b is a constant, then that is b to the u times the natural log of b, then times the derivative of the u. A special case of this is when b is e, and that's e to the u. The natural log of e is 1, so that part basically disappears there, and then you have the derivative of the u. So a very big difference between variable base constant exponent and constant base variable exponent. Let me ask you a couple other questions. Now, what if both the base and the exponent are constants? Like, what would be the derivative of e to the pi? Well, that would be 0, because e to the pi, if they are both constants, and when e to the pi overall is a constant, so the derivative of a constant is 0. So if they're both constants, then of course the derivative is 0. But what do we do if they're both variables? So if we had, like, x to the x power, or some other thing where we have a variable base and a variable exponent. Well, it turns out that neither one of these rules apply. How are we going to go at this? So it turns out that we can use a technique called logarithmic differentiation. And here's what we're going to do. Important part of this technique is this property of logarithms that you see right here. The log of x to the u is u times the log of x. Okay, and so let's go in here and see if we can do this for this particular one. So let's suppose that we take an expression that just has a base and an exponent, but both expressions, both the base and the exponent, are variable expressions. They both have x's in them. So let's make two substitutions. Let's let u be the base and v be the exponent. So u and v are both functions of x. We've made two substitutions. Now what we want to do is, we've got this variable up in our exponent. You got a variable up in the exponent and you want to get your hands on it. What do? Well, you throw a log at it to knock it down. In other words, what are we going to do? We're going to take the natural logarithm of both sides. And we use this property of logarithms that we just went over that says this on the right, then the natural log of u to the v power is v times the natural log of u. Alright, so that's it looks like we've made things a lot worse, but in fact we have been able to get the power down, which is going to be an important step for us. Then we want to take the derivative of both sides. If these two things are equal, then their derivatives are equal. So we take the derivative. Now, let's look what happens here. The derivative of log of y, we know, is 1 over y times the derivative of the y. Of course, the derivative of y we can write as dy over dx. Now, so we just use the logarithm rule and the chain rule right there. On the right side, we have basically a product is the last thing we have here. So we're going to use the product rule. So that's the first v times the derivative of the second, that's the derivative of log u, plus the second, log of u, times the derivative of the first, that's dv over dx. First times derivative of the second, plus the second times derivative of the first, that is the product rule. Now, let's do these derivatives. There's one derivative here that's left. The derivative of natural log of u is 1 over u times du over dx. Okay? And I'm going to finally, we're trying to find dy over dx. That's what we're looking for. So we're going to solve for that by multiplying both sides by y. Now let's go back and substitute what y is in there. I also wrote v times 1 over u as v over u here. Now y is u to the v, and I'm going to distribute that. Okay, well now when I multiply it by this first one, I have a u to the first in the denominator, so that cancels out one of these powers, or subtracts 1 from the power. So I have v times u to the v minus 1 times du over dx, plus I have the natural log of u times u to the v times dv over dx. And so this is what I call our generalized power-exponential rule. So it says if you got the derivative of u to the v, it's v times u to the v minus 1 times the derivative of the u, plus the natural log of u times u to the v times the derivative of the v. Does this look familiar? What happens if we apply this same rule and the function u is a constant? Well, then this du over dx is 0. And so this whole first term disappears. And what rule do we have? If u is a constant, we get natural log of u times u to the v times the derivative of that variable power. Hey, that's just the exponential rule. What happens, this is pretty cool right here. What happens if the power is constant? Then dv over dx is 0, and this second term disappears. What are you left with? Oh, if the power is constant, we bring the power down, it's v. We have u to the power of v minus 1, and then you take the derivative of that variable base. That is the power rule. Hey, look at that. That's the power rule. Now, by the way, we just proved that the power rule works no matter what. So I told you when we did this earlier, we only proved it for various special things. We proved it for the power rule. We proved it for integers, basically for the power is basically all we did, and maybe a few other sporadic ones. And then here, but this proves that the power rule works no matter what. Because nowhere in this derivation did I use the power rule, so I do not have any circular reasoning going on. We did use the exponential rule. We used the logarithm rule, which used the exponential rule. We used the product rule. Okay, but we did not use, and we used the property of logarithms, but we never used the power rule. So this proves the power rule in general. So now, finally, it's legit to use the power rule no matter what the power is. And we can use this more generally no matter what. Of course, we can apply this when we have variable base and variable power. So that's, and it's really just a combination of the two rules that we already know. You do the power rule, you do the exponential rule, and you just add them together. So let's apply that in this case here. So let's look at the derivative of 2x to the power 3x. Okay? So we apply it just like it's a power rule. We take the 3x in the front. times 2x to the 1 less power, 3x minus 1. That would be like, kind of treat it like the 3x is a constant. And then you take the derivative of the variable base, which is 2. So that first part gives you 6. And then, well, actually it gives us 3. And here we have a 2 and an x, so this makes this 2x to the 3x. Okay, how about the second part? Plus, we do treat it like we would an exponential. 2x to the 3x, the derivative is 2x to the 3x, times the logarithm of the base, and then the derivative of that variable power, 3x. That derivative is 3. Okay, so once again, from this step to this step, notice that we have a 2 and an x. That's the same base we have here, so it adds 1 to the power. So 3x minus 1 plus 1 more is 3x. So we have 3 times 2x to the 3x. Here I put the 3 in the front instead of a logarithm, and I have a 2x to the 3x. Now both of these have a 3 and a 2x to the 3x, so I can factor that out. And I'm left with, well, everything factors out here, so that leaves a 1. And then I have log of 2x. So the answer is 3 times 2x to the power of 3x times parentheses 1 plus the natural log of 2x. See if you can do that. Here's one very similar. Okay, why don't you go ahead and work this one, and then we'll check it here in just a minute. So work 4x to the power 5x, finding its derivative. Press pause now. Okay, so we can do this. Let's see here. Let's go down. Here. And work out a solution to this. Okay, so what do we have? We treat it like it's a, just pull that over for a minute. We treat it like it's a power, power rule. If it's a power rule, what do? You take the old power, the 5x, pull it out front, subtract 1 from the power. Now just to keep track of this, when you subtract 1 from the power, then you take the derivative of what would be the base for the power rule. What's the variable part for the power rule, which is the base. And that's the derivative of that part. So that's like it was a power rule. Bring the power down, take the derivative of the power, some 1 minus 1 from the power, and then derivative of the base. Plus, now we treat it like it's an exponential rule. If it's an exponential rule, remember the derivative of exponential is the same exponential. Out front you have the logarithm of the base. And then we also have a derivative of, in an exponential you have to take the derivative of what's normally the variable part in an exponential, which is the exponent, 5x. So there we have that. And let me copy and paste here. And what part changes? Well, the derivative of 4x is 4 when we take this derivative. When we take this derivative down here, the derivative of 5x is 5. And let's see if we can clean this up any. Once again, like the last time, this is notice that if we put this x with this 4, that's a 4x. Both of these now have the same base, so when you multiply them together, you add their exponents. The exponent of that 4x is 1, adds to this, gets rid of the minus 1. Okay. that for right now. And now let's see if we can do anything with this. Well, notice both of these have this part right here. So I can factor that part out of both, and that leaves a 1 here plus that. So I believe that is it. So let's check the distributive. If I take the 5 times 4x to the power of 5x times the 1, I get the first term. And if I multiply it by this logarithm, I get the second term. So that is correct. There is my final answer. So if you can do the power rule and you can do the exponential rule, we should be able to do that combination. In fact, if you want, you can think of always using it this way. It just, whether you have a power or an exponential, it's just some of those derivatives are 0, and one of the two terms will cancel out. Now, it turns out that this technique of logarithmic differentiation is sometimes useful above and beyond the idea of getting this exponential power rule combination thing I call the generalized power / exponential rule. Now, that is very important because the generalized power exponential rule, proving that was the only way we really proved that the power rule even works. So we really didn't even have the power rule established until when we proved this generalized power exponential rule. But we can use this technique of logarithmic differentiation. Now this is going to be a little bit harder one here. So this is kind of a nastier function here. We got a lot going on. Now there are multiple methods of doing this. For example, it's a quotient, so we could start with the quotient rule. Within that, we're going to have the product rule. There's going to be several other things going on here. So we could do several different rules and use it. But there's another way we can do it. So in this case, if we take the natural log of both sides, the properties of logarithms lets us take this thing that's more complicated on the right and sort of rewrite it. So we can rewrite it as everything's multiplied here, the 3 basic factors, 2 in the top, 1 in the bottom. So the ones in the numerator get their own logarithm, and the ones in the denominator get their logarithm well, but it has a minus 1 in front of it, plus 1 in front of the ones in the numerator. So that's a property of logarithms. And then we can use another property of logarithms that says we can pull the powers out front like this. Alright, now, so we've done some manipulation and sort of broken this thing apart, and the logarithms and their properties of logs allowed us to do that. So now we want to take the derivative of both sides with respect to x. Well, on the left, that derivative is just the derivative of natural log of y is 1 over y times the derivative of y. Now on the right, we break that into a sum of different derivatives, and then I'm going to use the constant multiple rule to bring the constants out front as well. So the derivative of this first part is 1/2 times the derivative of log of 3x plus minus 2. Then I've got the derivative of the second part, which is 2 times the derivative of log x, and the last part is -2 times the derivative of log of x minus 1. Well, then each one of these is a logarithm, so we can work out what that is. So each one is like log of u, so it's 1 over u times the derivative of the u. The derivative of the u is 3 here, so we have a 3, we still got the 2 in the bottom here, and then we got a 3x minus 2 in the denominator. The derivative of log x is 1 over x times this 2 is 2 over x. The derivative of log of x minus 1 is 1 over x minus 1 times the derivative of the x minus 1, but the derivative of x minus 1 is 1. So this is -2 over x minus 1. Finally, we want to multiply both sides by y. Of course, remember, we're looking for dy over dx. So y is the thing we want to take the derivative of. So we go back to here and remember that y was our original function, x squared times the square root of 3x minus 2 over x plus 1 squared. And there's a final answer, if you want to call it that, although we can definitely do some combining like terms here if we want by getting a common denominator. So let's practice our adding fractions a little bit. Okay, so if you look, our common denominator is going to have a 2, a 3x minus 2, an x, and an x minus 1 in it. So it's going to be 2x times 3x minus 2 times x minus 1. That's going to be the common denominator all the way across. How do we turn the first fraction into that denominator? We have to multiply the denominator by an x and an x minus 1. In other words, what's down here in the common denominator that's not in this one up here? Well, we take that x and x minus 1 and have to multiply it by the top as well. So that makes these two fractions the same. This one only has x in the bottom, so all of this, except for the x, has been added in or multiplied in. 2 times 3x minus 2 times x minus 1, we have to multiply the top by the same thing to make that fraction, the one in the middle, equal to that one. And for the one in the end, it already has the x minus 1, so what was additional down here that's not in the original was the 2x times 3x minus 2, so we must have multiplied the top and bottom by that to make those fractions equivalent. So now that we have a common denominator, well, actually I'm going to multiply them out first. So let's see, this is 3 times x is 3x. To distribute, that's 3x times x is 3x squared. 3x times negative 1 is negative 3x. Here I did maybe 2 steps in my head. I'm going to 2 times 2 is 4. We'll multiply that by every term as I get them when we do FOIL here. 3x times x is 3x squared times the 4 is 12x squared. I usually like to do the last next. Negative 2 times negative 1 is 2 times the 4 is positive 8. I've got negative 2x minus 3x, that's negative 5x times the 4 is negative 20x. And here I'm going to take this negative, I'm going to make this plus, take the negative in with the 2. So that's negative 2 times positive 2x is negative 4x. Then distribute that's negative 12x squared plus 8x. Now I'm going to put it together as one fraction and just add the numerators, which I've written down together. Now combining like terms, let's see, how about, looks like we got some squares. 3x squared plus 12x squared is 15x squared minus 12x squared is 3x squared. Or I should have just canceled the 12x squares, I guess. And then what do I have for x's? Let's see, I got negative 3x's minus 20x, that's negative 23x, plus 8 more is negative 15x. And then for the constants, looks like I just have the 8 here. And then we might see if we can put all this together as one single fraction. So we have the x squared, we have the 3x squared minus 15x plus 8, we have the square root of 3x minus 2, and the bottom we have 2x times 3x minus 2 times x minus 1, actually to the third power, because we actually have 3 of those together now, multiplied together. Alright, so that's kind of, that's a long problem. That was a hard one. But the logarithmic differentiation actually made it a lot easier than it would have been if I'd done it a different way. I could also done it, like I said, started out using the quotient rule, and within that the product rule, and so forth. And I don't know, you can try it the other way, and you can tell me if you think this was easier or not easier. But it definitely is a long problem. Okay. And here's one very similar to it. I'm going to leave that to you to practice and do it on your own. And then remember you can check it with your calculator by putting this in y1, putting y2 be the numerical derivative of y1, and then put whatever answer you get in y3. And by the way, up here I would have tried to factor the 3x squared minus 15x plus 8, but I don't think that factors with integer coefficients, so we're going to leave it like that. So that is the technique of logarithmic differentiation. It can sometimes be useful in these very long, harder problems, but it also proves the power rule in general, and it allows us to get to this basic rule here, which is our generalized Power-Exponential rule. So reviewing real fast again, the derivative with respect to x of u to the v power, where these are potentially both functions of x, is you do the power rule. V times u to the v minus 1 times the derivative of the u. Plus you do the exponential rule. Same thing, u to the v times the log of the base and then times the derivative of the v. Again, if the v is constant, the second part goes away and you just have the power rule. If the u is constant, the first part goes away and you just have the exponential rule. If they're both constants, everything goes away, you just get derivative of 0. But if they're both variable, you got to get both terms here.